All right, so this video is about derivative being used in sciences. And so we're going to start with just some unit problems just to get an idea of how to interpret this stuff and to show you how to set these up. So with all word problems, especially with these applications, even any applications, even if it's not a word problem, you want to start by defining your variables, writing out what they mean because it helps us to break the problem down. So the first one says if A represents the distance a ball has traveled, so we would say A is the distance a ball has traveled. And the more descriptive you are, usually the easier the problem is. And then there'd be units usually attached to that, like feet, miles, kilometers, something that represents distance. And then it says T represents the number of seconds. So T is a time, and it is in seconds. And then now we can use these to define or give units to our derivative of A with respect to T. So dA is the distance. It's actually the change in distance, and dt is the time. So now we can say that dA, dt represents the change in, and you just write it, in distance per unit of time per second. So that is our time. We actually do have units. So instead of time, we should write seconds. And you want to put at, because derivatives are instantaneous. They're at that point. We can use them to approximate. So you could also say approximate rate of change. But at dA dt represents the change in distance per second at t seconds. So you're going to plug in t. It's going to tell you a rate of change or slope, and that is the change at that time. All right, so let's try another one. So C here represents our cost, and so that would be in dollars. That's what we're paying with. X represents the number of units. So its units would actually be units because it's the things that we are making. That's our cost. And so dC dx as units would be dollars per unit. So dC dx represents the change, and again this one is about, if you notice the last one, A was the distance, but it's the change in distance per second. This would be the change in cost per unit. At X units. So again, you would plug in like 10 units and it would tell you the change in cost per unit at that units. All right, so let's try one to see if you can figure out how this works. We will do a cost function one in a later section, but for right now we're going to stick with a population problem. So it is estimated that T years from now the population of a certain town will be this. This should seem familiar. We've done this one before, but we're going to now add to it. Okay, so what is the change in population in the town from 4 to 6 years? So if they say change in population, they're not looking for a rate here. They're literally saying, how did it change? So if you plug in 4 and you plug in 6, it will tell us the population at 4 years, and it'll tell us the population at 6 years. So all we're literally doing is plugging it in to find out how many people there were at 4 years and how many people there were at 6 years. So if we plug those in our calculator, we get 10,816 and 11,236. So it looks like this. At 4 years, we're at 10,000. It went up here. So they just want to know, how much did we go up? How much did it change? So again, 10,816 and 11,236. So what was our change in population? So if we subtract those, it'll tell us our change in population. So this will work now. Okay, so we take that one, subtract that one, hit enter, and we get 420. So 420. And it doesn't say that there's thousands of people, but it's just people. And so what this represents is literally the change in P. 420 people. It's our numerator when we're talking about a rate. So if we want to know what's the average rate of change of P, that would be change in P over change in T. We want to see how is it changing. And so our time went from 4 years to 6 years. So that's a change of 2 years. That's our change in time. And our change in population was 420. So what we're saying is over this last 2 years, the population went up 420 people. So that's why we're getting a slope. That's all it is. When they ask for an average rate of change, they want the slope between those 2 points. So for 4, we got 10,816. And for 6, we got 11,236. So if you find the slope, you find the average rate of change. So it's 210. And then we put the units. So what are our units? So remember, we're supposed to write those down. T is in years, so it is time. In years. And P is our population. So that is in people. Unless it's an ant farm, but I guarantee it's people. So if you notice, the top is 420, that's people. The bottom is years. So this gives us 210 people per year. So we now know the average rate of change from 4 to 6 was 210 people per year. So now the question is going to change a little bit, and now it says, what is the change in population at 4 years? So now we're looking at an instantaneous, and that becomes our derivative. So what they're asking you to find is P prime of 4. And again, this is dP over dt, so we already know our units will be the same as before, people per year, because that's what we're looking at, derivative P with respect to T. So if we take our derivative, let's first find P of T. So P prime of T would be 2T plus 200, nice and quick. And we plug in 4. And so this gives us 208. You can see that it's pretty close. It's a guess. That's it. And so you can see our derivative of A is 208, and so that is the slope of our tangent. So at this point right here, our tangent line is saying it is 208, and the average rate of change was actually 210. So if you zoom in, you can see it's extremely close on there. It's only off by 2 people. That's it. It says we're doing short distances. Okay, so if they ask for the average rate of change, we're just doing slope. And if they ask for what is the change in population at 4 years, then they're looking for the derivative with respect to time in this case. All right, and then the last question is the population increasing or decreasing at 4 years. And remember, if it's increasing, our derivative, in this case P prime is positive. And if it's decreasing, our P prime is negative. And since it's positive, it is increasing. It also just says it is. Our population, right, the change in population is 208 people per year. Our average rate of change was also 210 people per year. So at 4 years, we have 208 people per year increase. That's our change in population. So just like our dC dx represents the change in cost per unit of x per unit at x units, our P prime represents the change in price per unit of time at t units. So there you go. Thank you.